Okay, we are back in live mode. Hello, everybody, and welcome to our training series dedicated to turning biodiversity observations into insights. And it is my absolute pleasure to be your host again for the next hour and a half, when we'll be learning about innovative ways of investigating zeta diversity using species occurrence cubes. We have our amazing trainer with us from South Africa here, Sandra MacFadyen, and she will be just sharing again a little bit of her expertise. So we are grateful for taking the time to do it. If you have questions for her, please use the Q&A option, and we'll try our best to answer all of the questions. So just for the people that are joining us for the first time, a little bit of context about the training series, which is organized in the framework of the B-Cubed project, which is a project funded by European Union, Horizon Research and Innovation Program. It is a project that is aiming to improve the integration of data from on biodiversity from different sources, making it more accessible, more rapidly, and more reliable, using repeatable workflows, which is what we'll be discussing about today as well. If you want more information on the project, its aims, its outputs, you can find that on the project website, available at bcubed.eu. And there you'll find amazing things that are being worked on and developed by an amazing team of people, very passionate people that are coordinated by Quentin Groom from Meissen Botanic Garden in Belgium. And this big team of amazing people are based at different institutions across Europe and also beyond Europe. As you have noticed already, our trainer today is joining us from South Africa. So please do check out the website and everything that is done within our project. If, again, you're joining us for the first time, just please know that we already started this training session a few weeks ago. We had some amazing talks about species occurrence cubes and how these cubes can be used in different contexts. For example, in biological invasions. You can find recordings and informative materials on our website, again, under the section news. And please do keep an eye out on what is happening the following weeks, because we are not done yet. There's still more exciting stuff coming your way. So today we'll have Sandra talking to us about this dissmapr automated workflow. Just before I hand over to Sandra, in case you don't know her work, she's a postdoctoral research fellow based in South Africa at Stellenbosch University. She's an amazing person and an amazing researcher. She has a joint PhD in botany at Stellenbosch University and also in landscape ecology from Vrije University in Amsterdam. She holds a master's degree in geographic information science and various postgraduate qualifications. She's passionate about nature conservation, and her research is focused on advancing biodiversity monitoring and conservation, particularly in large protected areas, as she is based in Kruger National Park, and she has been working there for almost 30 years. So I'm really, really happy that she is joining our training session again, and she's sharing a little bit of her expertise on this research on ecosystem dynamics at the large spatial scales using a lot of complex methods that she's making sound very easy, like this complexity theory, mathematical ecology, spatial temporal statistics, and things like that. So thanks again, Sandra. Really, really delighted that you joined us again. Before I hand over to Sandra, I would be happy if you would take the time to just answer a couple of questions, which would help us get an idea about the participants that are joining our sessions. And these quick questions are just related to the countries in which you are based, the level of your careers that you're at, and also the main sector in which you're performing your activities. As mentioned, it's completely anonymous, and it will help us just get an idea about the audience that we have joining us each Friday afternoon. So please do take a couple of minutes to answer this quick poll. We do have nice distribution with people that are in the early stages of their careers. We have master students and PhD candidates with us, postdoctoral researchers. So this would be the main categories, but also people that are more advanced in their careers and have a bit more experience. So we even have a couple of people with more than 10 years experience. So it's good that we have a very nice distribution, different levels of expertise in the room. A lot of researchers with us and people working in academia. So I think maybe half of the people joining, but also happy to see that again, we have with us people from the government and public administration, NGOs, and the private sector. Great. Thank you so much. And now I will just hand over to Sandra to introduce us to the topic of the day. Thank you, Sandra.
Thank you, Christina. Thanks so much for that introduction, and thanks everyone for joining me today on this Friday the 13th. Some people say it's lucky, so let's go with that. I'm going to quickly share my screen. All right. So as Christina has already mentioned, today I'm going to be taking you through a new package called dissmapr, which is an automated workflow for computing computational dissimilarity and biodiversity turnover. And as she's mentioned, we're part of a few presentations that are given every Friday as part of the B-Cubed hands-on training. And today what I'm going to do is, the schedule is to first give you a brief introduction to what is community or species turnover, the limitations of pairwise measures like beta diversity, and introduce you to might be a new concept to you, the idea of zeta diversity as a multi-site generalization of beta diversity. From there, I'll take you through some of the logic behind a multi-site generalized dissimilarity modeling. So some of these words sound big, but we're going to work through them together, and hopefully you'll understand that by the end. And then we're going to go on to a hands-on session with dissmapr. So most of the session today is going to be hands-on. I'm just going to give you a brief theoretical introduction. So while I'm presenting in the background, if you haven't already got R installed and RStudio and RTools 44, version 44, you can go ahead and install that while I'm talking. And I'm on my own today, so I'm going to try and answer the questions in regular stops. So especially when we start working hands-on, I'll stop every now and again to see if I can answer some of your questions. If I can't get to them, they will be placed in in a Google Doc, as I understand it. All right, so Christina has also already told you that we're part of this B Cubed project, which is Biodiversity Building Blocks for Policy. And what's exciting about it is that it's made up of 9 different countries and 12 different institutes, which I think is quite a feat. And this is part of the B3 verse, which has come out of this B Cube project. And I'm going to be talking today about compositional dissimilarity, the dissmapr package. A few weeks ago, I gave some introduction to the invasive mapr, and there are a number of other packages, as you can see from this diagram. And I think the last session, Ward is going to take you through the B3 verse and help you get to grips with what has been developed. So this is the website. I'll pop it into the chat just now. So this one is where we're going to run through the different tutorials. So there's vignettes on there that we're going to run through. I've created a script that we can go through it together, so you don't have to run through the R Markdown. And then there's also some basic information there if you want to catch up afterwards on what exactly is a dissimilarity cube. I'm not going to go into that in too much detail, but there is a lot of information online and on the B Cube site, so please have a look at that. So to focus quickly on the understanding behind the development of this dissmap package, we need to first understand what is species turnover. So I'm going to take you back to Ecology 101, and species turnover or change is a change in the species composition across space or time. So it's not just about species disappearing, it's also about the reshuffling of who lives where, which as you can imagine means that there's something going on in the environment that's causing this to change. So it captures a deeper level of ecosystem change. So for example, in Kruger where I'm working, if you look at one area, it could keep the same number of species, but the key species may be replaced by others. So that leads to shifting food webs and habitat functions. So as you can imagine, understanding this turnover is critical for tracking true biodiversity loss beyond just simple species count. So it also helps when planning for connected habitats and refugia, which is especially important in the face of climate change. Parks don't move, but animals do. And if the climate shifts and the habitat changes, they need a place to go. So redesigning corridors is something that's really important in this changing world. So to give you a brief introduction to the species turnover, we have to talk about the different levels of diversity. So when I say alpha diversity, it's a simple count of richness. Beta diversity is compositional turnover, but it describes how many species differ in composition among sites, but only 2 at a time. So depending on the method that you're using, the underlying value is dissimilarity. So that's where we get to this measure of dissimilarity. So if it's a 0, it's essentially they've got identical species. If it's 1, they could have completely different species. So to put it into context, if, for example, you had a site layout like this, so you've got 7 sites, so this could be a table as well, a matrix. At that site, you've got each site has got a certain count of species, so that's your richness, your alpha diversity. Then if you start comparing 2 sites, you have what's called beta diversity or turnover. And it is only 2 sites. You keep comparing multiple ones. They don't need to be next to each other. And if you have sites that are very much the same, they would have very low beta diversity. If you have sites that are very different, they would have a very high beta diversity. So that is what I talk about, high and low, when I'm talking about diversity. But as I mentioned before, this only gives you a pairwise estimate of turnover. So it's a simple site-to-site difference. So it looks at each site, it compares it to each other site, and then it averages that. So you're only getting that turnover, and that can make rare or local species outweigh the sensitivity to diversity. And uneven sampling really does inflate this problem even more. So you would have large turnover when it's just rare species that are localized in one or two sites. And this tells us very little about the stability of the core or the widespread species that underpin ecosystem structure and function. So as you can imagine, the rarer species, they're rare because they're often sensitive to change. So these are our canaries in the mine, early warning of things that are happening in the system that are making those species disappear. But as you can imagine, if widespread species start to change, that means that there's a really serious thing going on in that area that you're working at. So how do we go beyond this typical measure of beta diversity? We're only comparing site with site. And that's where a concept zeta diversity comes into play. So it's a multi-site generalization of beta diversity. So it counts how many species are shared across a different number of sites. So it can be between 2 sites, 3 sites, 4 sites, and so on. And this is the original paper. This is actually the head of our lab, Kang Hui, Prof. Kang Hui. So if you want to read up on that, there's a link to it. And yes, as I said, it's done that. So Zeta 2 is essentially just a pairwise case because it's 2 sites compared to each other. So it's the same as your simple beta style turnover. Your lower orders reflect the local or rare turnover. So as I said, the beta diversity is quite weighted to rare species. And then your higher orders reflect this widespread or core persistence of species. So typically, as the number of sites increase, your zeta declines because there's fewer species that are shared amongst more sites. And this helps us separate this local reshuffling from system-wide community change, as I mentioned before. So again, to put it into context, I'm just going to run through this again. Here's your sites again. You've got your 7 sites or your tables. You've got your species richness, which is 1 site. You're just counting the number of unique species in that site. And it can be across your whole grid. Then you've got your beta diversity, or in the concept of zeta diversity, it's your zeta order 2. So those are 2 sites that are compared. As I said, they don't need to be next to each other. They can be throughout the thing. Then you've got a new concept, zeta 3. So this is your zeta order 3, where you're comparing 3 sites. And they can also have different structures. And zeta 4. So here you've got 2 and 2 equals 4. So those are 4 sites compared, 5 sites compared, 6, and so on. You get the idea. So to put this into context, when we start doing the hands-on session, I've spoken about zeta order. So zeta order 2 means the number of sites that compare. But if you have a zeta value of 40, that means on average, any 2 sites share 40 species. For zeta order 4, it means that between every 4 sites, there are only 20 species that consistently show up, and so on, until you get to the end where, in this case, we had 7 sites in our example. So if there was a zeta diversity value of 5 at zeta order 7, it would mean that only 5 species occur everywhere across our whole study. So to break this down, as mentioned already, that your lower orders then represent the rarer localized species, and your higher orders the more common and widespread. But why does this matter? So for rare species, as I mentioned, they often respond first to any emerging stresses. So they're your canaries in the coal mine. And they highlight these local refugia and microclimate dependence because they're very sensitive to these changes. And they can flag early reorganization risk. For the common species, they represent the most biomass and essentially then the underlying ecosystem function. Shifts will then indicate a deeper system level change. And by identifying or separating these, we can help separate the signal from rare species noise. All right. So zeta diversity on its own doesn't tell us much because what we need to know is what is driving that change to see if we can alleviate those issues or start doing conservation planning where we extend boundaries, for example. So it tells us how many species are shared across these many sites. But coupling it with a modeling exercise or function called multi-site generalized dissimilarity modeling, your MSGDM, this tells us which environmental covariates and space and distance explain why these sites share fewer species. So together we can work out what drives this reshape of communities and whether they are mainly affecting local species or widespread core species. So we're going to do this together. So again, this is the layout of the workflow, the online documentation about the dissimilarity cubes that I mentioned. And this is what we're going to go through once I take us out of this slideshow. On the website, we've got different tutorials. So if you click under the article section, you've got different articles that we're going to work through in one script. But at any stage, you can go through there and have a look. It's got a lot of descriptions there about the results. So it'll help you understand some of your outputs. We're going to be talking about it as we go through our script now. But if you want to look at more detail, you'll see that there's a lot of descriptions there. Then obviously under your package index, your reference section, it gives you more information about the different functions. So I'll take you through that as we work through the script. But at any stage, if you're not sure what a specific parameter means inside one of these functions, you can go onto the package website and click on that. So they're split into three main sections. The first is the core functions that are embedded within the dissmapr package, but they rely heavily on zeta div, which is a package that was built by Guillaume Latoum, as well as the MSGDM workflow. So the functions that are there wrap around existing functions that are in this zeta div package. And then there are a number of different metrics. So we're just talking about dissimilarity, but there's a compute order-wise function that you can choose essentially any of these metrics, or you can make your own, and you can run them in this zeta diversity manner. So more than one site. So this is a brief look at the workflow. I'm just checking on my time. Okay, that's fine. All right, so what we're going to go through together, just to give you a quick overview. So we'll go through setting up the dissmap package, which is sitting on our GitHub site on the B-Cubed website. We're going to take you through some accessing of data. So you'll see the function there that gets occurrence data. We're going to run through an example from GBIF where we extracted some butterfly data. But if you have your own data where you've got a site by species matrix, you're welcome to use that as well. It then takes us through a step of linking that occupants or occurrence records to environmental data. So we're going to work through existing packages like Geodata and the WorldClim database. If you have your own local raster data, that would be really great. And I'd love to hear from you how it works out. But obviously, the more finer scale your environmental data that you're going to be using as predictors are, the better. Higher resolution in terms of time and space. We've then got functions built into dissmapr that helps you format the data. So a lot of my students have a lot of problems trying to actually get their data into a format that we can use in any of these analyses, not just through dissmapr. So there's a built-in function that will help standardize those tables for you. So we'll go through that. As I mentioned, there's a compute order-wise function that actually does some different metrics for you. We're not going to run through that today, but you can do it on time. We're going to run through computing this zeta diversity and combining it with this multi-site model so that we can pull out what are the drivers of diversity change or turnover at different levels. We've then got other functions in there that can help predict that. So once you've built that model, you can take that and predict it onto a map. If you have the same, well, in this case, you will have the same environmental variables. But if you want to project then into future scenarios, we will then take environmental data that's changed. Or if you've got future climate predictions, you can substitute those out and run it again and look at how those patterns will change. Then we've also got some functions in there that can help classify bioregions. So that's clustering your predictions of this zeta diversity or species turnover into spatially coherent community bioregions. So there are different methods in there that we'll walk through that you can choose that will do some clustering so that we can look at the general bioregions formed. And then importantly, we've got some functions that look at bioregion change. So essentially, this is what we want to know in terms of climate change worries that we have at the moment. Where are these biomes going to shift? And this bioregion change will help you do that. Then we've got a wrap-up function that just does some summary of results. And the dissmap package on its what it actually does with the zeta diversity stuff is that it allows you to run it, instead of running it one at a time, you can run a whole bunch and then you can output the results in the summary format. So I'm gonna show you how to do that. And before I do, I just want to quickly talk about this formatting. As I mentioned before, this seems to be quite a big stumbling block for students when they first start working on real data and trying to look at mapping these species turnovers or diversity changes. So once again, we've got our 7 sites. So each of those sites has a species, and those species occur in different numbers across those sites. So if it's a lighter color, it means that there's low numbers of that species. Darker color means there's higher numbers of species. What I didn't put in here are some white blocks where actually that species doesn't occur, but you get the idea. So this is your typical matrix. What we want, though, is to turn this into a cube. And to do that, we need to have environmental variables that we've plugged into this. So those sites have a certain suite of species and certain numbers, but those sites also have different environmental variables. And this is where the link comes in, using the model to look at how those changes in the species composition link to environmental variables. Okay, so let's start with a hands-on session. I'm going to go out of this presentation mode. Let me check quickly if I have another slide. Okay, there we go. So that's just the website that we're going to be working on. Okay, I'm going to put into the chat quickly. Let me quickly check if there's any questions as well. Put in there some of the links. All right. I don't see any questions. So if you do have questions, you can, I can answer them quickly. But here is the website. So that is the tutorial that we're going to be going through. So if you click on that, you're going to get this. Okay. Yes. All right. So this is the interface that I was showing you. You've got your reference, which are your different. Let me just make it a bit bigger. Where it gives you an explanation of the different functions, so all of the different parameters in there. And here are the different articles that we're going to work through. So getting started, etc., etc., etc. This is the link to this information on the dissimilarity cube. And importantly, here is the script that we're going to be working on. All right, so I put it onto the G drive, but I'm going to see if I can attach it. Yeah, it doesn't make it attach. Let's see. Copy it. Might be too characters. All right, is everyone able to get that script? Oh, sorry, yeah, I found the questions. I was looking under the chat box. So yes, we've got two questions while you guys are accessing the G drive to find that script. So Antonio asked, so sites will turn into the space component of the cube. If you have the latitude and longitude, yes. So you need to have the latitude and longitude coupled with that matrix. So each site needs to have its actual position. Except denied. All right, so everyone should have opened this R script now. It's quite comprehensive. I've built it this way because I want you to be able to follow this at home on your own, because the real value of the dissmap package will come from you using your own data. So I put my contact details here. You're welcome to contact me if you're running through your own data and you want to get some help on that. I'd be interested to hear if there's any bugs as well, and also to see if the outputs make sense. So here I've also gone and put the websites that are important for you to use. And yeah, you don't have to read through all of this. It essentially just tells us what we're going to cover in the script. So I already mentioned that we're going to walk through the whole workflow together. And there's a bonus section at the end. So I'm not sure if we'll get there, but the bonus section is going to take us over projecting into the future. But it is there for you to work through on your own if we don't manage to get there. All right, so let's start off. If we go down to, all right, we go down to line 87. So if you want to create your own directory, if you want to keep all of this from the tutorial in a different directory, you can just quickly change this my directory to something else. So this is the one that I'm going to use. So if I run that, is it still very small? Okay, so let me try and make it even bigger. If I make it any bigger, I will only see one R on my side. So please, this is okay. Everyone okay? Just put a thumbs up or something if it's too small still. All right. So in this case, I've created this, I've just specified what is the working directory that I'm going to be using for the duration of this course. So I'm setting my working directory. And then I'm creating a whole bunch of folders just so that we can keep it separate. And if we want to go back and check, we can go back and check to see what the outputs are. So there it's creating this dissimilarity training folder, the data folder if we want to put our plots, if we want to have checkpoints along the way. So it's just going to create these different folders. And then it runs through some housekeeping. So this is just a function that helps us separate the different sections in the script so that you can go back and start making, if you want to go back to a section and just look at the outcomes, you can do that. So yeah, I'm just running this function so you can just run all of this until you get down to the line 138, and it just tells you there that this is the working directory that you're in, and this is the basic output. That's what that announce function is doing. It's just letting us separate that. So it's just to keep it neat as we're working. Then the first part comes into installing and loading these packages. So obviously we need to install the dissmap package, but sometimes to make it a little bit easier, we can go through loading some other packages first. So if we go down to line 162, it's this announce function. As I said, it's just separating it in the console for us. And then there's a number of packages here that are quite important, and sometimes it helps to have them loaded before. So we're just going to run that to say these are the packages we need, and then it runs through them to say, all right, if I don't have these packages, install them for me. And it will check. So in my case, it says that all the listed CRAN packages are already available. On your side, it might say something else. So it might start installing the packages. So if it does do that, please just accept, and then it will install those packages that we need to go forward. Once you have that, then you can install dissmap. So as I said, it's on the B-Cubed site. So that's on the GitHub site, and we use the remote package to do that. So this section here, all it does is if you haven't got dissmap, it's going to install it for you. It's not going to do anything for me because I have already got it installed on my computer. I'll give you just a few moments to make sure that everybody has got that loaded and installed. If you have any problems or questions, just put them into the chat or the question answer box. It would be nice if you can change the cube from BB to BDC by diversity cube. All right. Please always raise your hand. Okay, so if you get to the section, Paul's got a problem there where it says error in library dissmap. There's no package called library dissmap, so you have to install it first. So this part here installs the dissmap package, and I specifically put in there dependencies false because I wanted it to go a little bit quicker. And there's also someone that's having issues there that says the package error, dependency C valid, entropy, factor extra, geosphere, are not available for the package. So if you're getting errors with a specific, so the one that Paul had where he said that there's no package called dissmap, go back to lines 188 to 190 and rerun that. So we need that to get installed. If you have a message like this anonymous attendee had, where there's a number of different packages that it says it doesn't have, so it's not available for dissmap, you must install those. So just go and copy that whole line and put it into something like this. So if you copy those ones that you don't have, put them in here, and then rerun this section, then it will install those. Okay, so I'll give you a few minutes. So everyone who has dissmap installed. I'm not sure what Daniel means by change the cube from B cube to BDC. I think you mean the B3, change it to BBC. This is a Horizon Europe grant, so we're stuck with that, I'm afraid. But we can change it in the dissmap package. We could have something different there. Okay, so you can also change that dependency is true. So thanks, Catalina. If you still got problems and you want to double check it, you can use the dependency true. So yeah, change that to true. That's what I was busy saying earlier, and I lost my train. So if you change that to true, it's going to install all the dependencies. But there are a lot of dependencies, so this package is still in its infancy, so there's going to be a lot of bugs. And I'm busy streamlining the different packages that you'll actually need. So yes, if you're still getting these errors with the large number of packages that you still need to install, just change this dependency to false, change it to true, and then retry it. Yeah, thanks, Kathleen, for that. All right, so I think we're going to carry on. If you still haven't got it right, we can try and address some of it at the end if we've got time. But for those of you who have it installed, you can now load the library for dissmap. There are these other packages just to make double sure that they are there. These are really important ones. So just run those and make sure that they're loaded. And then we can start working with our data. So this function is the get occurrence data. It's built into the dissmap package. And if you have your own data, so if you've got a CSV file where you've got latitude and longitude columns for your site and your different species or taxon in a column, you can also have it in so this is called a long format. You can also have it in a wide format. Okay, so those of you who are having trouble loading dissmap, what you can also do, if it's not working, is just download it from the GitHub site and then try to install it manually, if that works. But it can be because there are, as I said, a large number of packages that it requires to run. So I will be streamlining that definitely. All right, so this section, as I said, we're going to run through Catalina, just to repeat what I said about the format. So in many cases, you'll get your different formats for the data that you collect. So when you're in the field, you'll probably have a table that's got the site number and then a column that says species, and then all your different species are in there, and then maybe a column next to it with the abundances. That is called a long format. Whereas in most cases, well, definitely in dissmap, we need to have the wide format going forward. So that means instead of having your site, species, and abundance, you would have site, and then your columns would be your species names, and the values within those different columns would be your abundances. So that's what I mean about long versus wide. All right, so this data set, GBIF butterflies, it's already loaded into the dissmap package. So if you've got this, if you successfully managed to install it, this will come automatically with the package. If you have your own data, you can use that instead. What you can also do is you can load a URL from GBIF. So this one is just loading the butterfly data into my session. This is the function that I was talking about that takes that data and just checks that we've got everything named correctly. So it's not formatting it yet, it's just making sure that we've got all the names set up the right way. If it's not, it will help fix that. So in this case, we put data, and I said the data type is data frame. If you had GBIF data and you went and searched for that, you always get your URL where that data set is sitting. You can change this to the URL and you just paste it in there. So you don't actually need to download your GBIF data. It will take it directly from the URL. So here I'm using the function get occurrence. It's from the built-in data set, because it was quick. As I said, here is your option to use your different data. As I said before, if you go up here to references and you get to your occurrence data, each of these parameters are explained. So if you're using GBIF, you can put your zip URL, directories, and certain things. So yeah, this is probably an important step. So let me just spend 2 minutes talking about this. So it will automatically look for typical column name. So for example, if your column name is called site, you don't have to go and put in site because that's an obvious one. It will check it for you. If your X column, which is your longitude, is called X or long or longitude, it will automatically get it for you. And the same with the Y. Also species column. If it's called species column, it's fine. If it's called verbatim, if it's called verbatim name, which is what the GBIF calls it, you don't have to worry. But if it is something different, because I know some people name their columns strangely. So if it's not one of those, it will give you an error that says that I can't find this column. Then all you do is you take the parameter and you put it in. So if you know what the names are and they're different from a logical setup, then you can put them in on your own. All right, so mine was fine. So my occurrence data, I've got 81,000 rows and 52 columns. So this is just a way to visualize it easier. I've got a lot of species, so I didn't want to put the whole data set in there. Also the head, just the first 2 lines of those columns, because if I put all of them in, you wouldn't see anything. So this is the example I said. It's called site ID, and present absence, X, Y, the GBIF ID. So this data, as I mentioned, is straight from GBIF. All right, then we go to our format function. So this is going to then format your data into the site by observation table and your site by species table. So if we run through that, and we take that data set we just created, so that's our object that we just created, and we look here, and this is the name of the species. So if it's got a strange name, I put this in here just so that you could see, but it would do it automatically. The same with PA, which is present absence. If it had that, it would do it. And it's telling it that it's a long format. So as I was saying, this is a long format, but you don't have to do it. It will try and detect it itself. So if you don't put those in, it will do it. Something like this. All right. I need to fix that. I will ignore it. All right. So what it's done now is it's created a list with a site object, which is a data frame with so many observations, and a site by species matrix. So this is your wide format that I was talking about. So we could leave it like that, but just to make the coding a bit easier, I've just turned this into their own objects. So rather than using them as an item in a list, we're just going to create new objects from it. And it's telling us there that we now have so many rows and columns, and this is what it looks like for the site. All right, so that doesn't look very different, but it's taken away all the other info. It's just kept what we need going forward. So these are your site IDs and your lat longs, and how we've got this, which is your wide format. So you see site, longitude, latitude, and now all of the species names of the columns, and it's a yes or no if it's there or not. All right, so now these things you have to change according to your data. So in this case, I've got my site ID, my X and my Y in my site by species table, and then my species columns start. So when I want to look at how many species I have, and I can just count the number of columns, but I can't count those 3. So in this case, I've just removed the 3, so that now I can see that I have 2,868 species in this data set. If I want to get the actual species name, I can do a similar thing. So you'll see I switch it around because I want to show you that there are different ways to do exactly the same thing. So you'll see sometimes I use one thing and another thing. So that's doing the same thing. It's taking away the first 3, and now I've got all my species names there. So that's just taking it from the column. So all of this is just a way to double check. It's always good to double check as you're going through anything to see if there's any weird mishaps that happen along the way. You don't want to get further on and then nothing works, and then you realize, oops, it was just some small thing that happened in the beginning that threw you off. All right, so now the next one, if we go down to row 360, we're going to now create an area of interest. All right, so in this case, the dissmapr package comes already with an outline of South Africa. So this study is specifically in South Africa. If you have your own data, you would replace this with your own shapefile or area or extent. You can also just put in an extent if you don't have a shapefile. Here you specify the grid resolution, and so the reason we're doing this is that we've now got this list of species. But they're at a site level. So those coordinates are points of specific sites that people visited. But if we want to start generalizing it, and especially if we're running an example here where we can't have these individual sites, we want to make grids that we can accumulate these data into and then run it. So in this case, I'm setting a very large grid. I'm setting it to basically 50 kilometers. So it's like a 50 by 50 kilometer grid. So this is in degrees. You can change this to meters, but I'm not going to go into the whole projection thing now. I'll talk about it a little bit later. All right, so that's the size of the grid that you're going to create. I'm just making a vector of my outline so that I can use it later for generating a grid. So it takes that grid resolution that I've set. It takes the existing projection from that vector, and it creates the template. And then I'm just creating, what this does is it makes all the values in this grid template. So we've now got a grid over South Africa that's at 0.5 degrees, so that's 50 kilometers. I'm just making all of those values 1, and I'm masking it by that vector that we created, the polygon. So now I have a grid that is just the outline of South Africa at this 50 meter resolution. So as I said, you can use your own data. Now we get to the point where we want to aggregate these data that we have into the grid. So we go down to 414, sorry, and we run this function, generate grid, and we put in there the parts of the data frame that we just created. So remember our site by species? That was our wide data frame. I'm just telling it that the latitude and longitude in these columns, this is the grid size. So remember we set that in the beginning. This is the columns that you want to sum. So it's everything from 4 onwards. Remember site 3, 1 to 3 were site and latitude and longitude. And this is setting the projection. So this is just a geographic projection. You can change that, and then it will be in whatever projection you choose. All right, so it starts generating this 0.5 degree grid. So it will take a little while. The finer you make that grid, the longer it's going to take, obviously. All right, done. So we can just check what we've got there. So it's again a list, and it's got 4 different objects. Your grid R, which is the raster, your grid SF, which is a polygon essentially, and then some tables, which is your grid species and your grid presence and absence. So it's similar to what we had previously with site species, but now we've got grid. So instead of having a unique site ID, we've now created a unique grid ID that is at a higher resolution. So it's summed all those species there. So you can, once again, just to make this easier, you can use it as a list, or you can just create objects from it. And we can double check that now the dimensions of our grid, we've got 1,110, right? Grid. There we go. And go. Sorry, so we got 415 sites, and we still got 2,870 species. So let's check this. Let's go down to 460, line 460. You run that. And this is just a plot. Just takes the new grid polygon that we created, this grid by species matrix, and puts in down here the outline for South Africa, just so that you can put it into context. So you run that, and then move this down. All right, so there you'll have this output. So it should look something like this. So this is still a matrix. It's just the observation density. So it's the number of observations. It's not species across Africa. So that's to confirm that everything worked. And then we carry on. And now that we've got that, we can start working on some basic descriptions of species richness and observation count. So this is a big issue when it comes to doing these type of analysis at the scale with cheapest data, is that there is an unequal sampling effort. So especially in Kruger, for example, all of the records from citizen science will be along the road. So if you were to take that data and just look at it at face value, it would look like the roads are the most diverse areas, but tourists are not allowed out of their vehicles. So it's giving you a false impression. So it's important to capture that. So we run from 500. I'm just going to create a square root of these just because there's quite a large number. So just for the mapping of it, it makes it easier. So your grid has already calculated this for you. So if I just put that in the console there, you see your grid. Your grid is going to calculate that now. So let's do this. Okay. And there we go. So now that we've plotted it, we'll have your sampling effort. So that's what we had before, just the count. And then over there, we've got the species richness, square rooted. So that's the number of unique species per 50 by 50 grid, square rooted, just so that it looks prettier on the map. Now we go on to extracting our environmental covariate. So we go down to 561, just to run that. And the function we use there is called getEnviroData. All right, so this function, it allows you to take data from different sources. So you can go and take, let's see quickly. So we go to getEnviroData. So you can use geodata or local data, and then you can supply with spatial raster. So if you've already got a raster stack with a number of different environmental variables on, you can use that. That will be much better than using these prepackaged ones. Somebody asked me in the previous one of the previous lectures that I gave for the dissmapr package. So I'm not sure if that person is here today. The question was, how do you link these environmental data to the species in time as well? So in this case, we're just looking at a mean. So it's the average, if you're using bioclimate data, the average long-term temperature or the average long-term rainfall. But these species records, especially if you're working at a local scale, they come with a certain time stamp. So you collected that species on that day. So it's unlikely that you're going to have the correct environmental data for that specific day, but you can at least narrow it down to the year and the month. So that's where the value of using your own data comes in. If you import your local raster that's got the year, like a whole year's worth of rainfall for the different months, then you can put that in here, link them so that they are extracted into the table with your sites and your species. And then you can just filter by the link between the name and the date. So if your column's name is 2010-03, that's March 03, then you just filter out for the records that link with that. All right, so we run this. I'm using geodata, I'm using the bioclimate data. Once again, I'm taking just the species columns. These are extra columns, I want to keep these. So if you don't put that in, it'll still run, but it won't keep them. All right, and it's gone. All right, for you, which I must mention, for me it went very quickly because I've already run this and it's actually got, I've already downloaded this geodata into onto my computer. For you, you're probably going to have a little window that jumps up and that wants you to download that data so that you can use it. You only do it once. So when you do this again, and provided that your locations are the same, it won't do it again. Right, we have a question. So basically, we are adding this third dimension to our cube by extracting the value of each environmental value for each of the cells exactly. So this is where that animation that I showed, where you've got the environmental data, this is now your cube. So you've got your sites, your species, and your environment. Okay, so mine went really quickly. Yours might be taking a little while to download. I specified the resolution here at 5 so that it would go a bit quicker. All right, so mine worked, and now I'll have a look. I've got a list. So I've again got a spatial raster, but it's now my environment raster. I've got my site, which is a point, a vector, and I've got my environment data frame. All right, so what do those look like? Let's go and have a look. Oh, this step here, as you'll see, bioclimate has these strange names. Any of you who have worked with it, you'll know. They just call bio 1 to 19. I know that that's the name of them. So I want to know that it's temperature, rain in the driest month, etc. So I'm just renaming it. So those are the names that I know, and I'm renaming it. I'm creating objects from it, and I'm checking to see what I've got. So now you'll see the grid ID, the centroid, lat, and long. So remember, we generalized. We don't have site and lat long anymore because we're taking the centroid of the grid that we created. And now we've got those different things. Why didn't it rename? Oh, I'm not sure. All right, it's probably something small. But you'll see here, this is exactly what we wanted. So the names didn't change, but it doesn't matter. Okay, we did that. Let's go down to expecting it. So we always want to double check. So at line 615, we'll look what we've got. There, as I said, that's it. Let's do a quick check. So instead of plotting the raster, we're going to plot the data that we extracted. So it needs to look like our temperature data. So yeah, I know it does look. So that means that we took that table that's got the species and sites, and we just mapped that part to see that it does make sense. And then another question is, in which way does the model help with citizens' data bias? So it doesn't. There is another package that that is looking at quantifying these bias, and that I think Ward's going to cover it in his session. But if not, there's a lot of information online with regard to that package. It just needs to be something you must be aware of. When we go into the modeling behind it, the environmental variables, then we deal with it. So up to this stage, we haven't dealt with anything. All right, so this is now just double checking and combining. So now we've got our observation and our richness in there. This step here, I'm rushing through it now because I don't want to really talk about projections, but when we go later into the other stuff where we're looking at distance measures, we need to have a cartographic distance so we can have a projected meter system here. So this is just your equal area projection. So just run from line 683 all the way down to 707. So that's just going to attach the meters projections in here. So your longitude and your latitude. All right, so I'm going to skip this step and you can do it on your own. No, actually, I really need to do it. So this, what it does is it removes strongly correlated variables. So you can run it, but we're not going to talk too much about that because we're running out of time. So you can go back and start from line 725 and just run all the way down to 714, 13. So this is just, removing the predictors that are very correlated, which is something one does. So here we go to calculating the expected zeta decline. And so this is the actual zeta part of it, and everything else has just led us to this stage. All right, we check that. And this is a function directly from zeta div. And it's taking only the species again, and I've specified orders 1 to 10. And it takes a little while to run. The more orders that you do, obviously the longer it's going to take. And we should get a plot. So that function, if you want help with it, you can just take this and put it into your console, question mark, and then paste that. And that will take you to the zeta div package that will explain each of these different functions to you. While that's running, I'm just going to quickly flick back to our online setup here. And underneath the articles, the vignettes there, if you go down to zeta diversity, so we've gone through all of those steps. This takes you through that whole section with explanations. So if I don't have time to go through everything, I've explained it all here, and I've explained how do you interpret these different graphs that are output from there. The same with all the other functions as well, the zeta decline, and each of these are explained in a lot of detail about what they mean. So if we don't get to it, we're running out of time already, you can go back and look at it and read it online, and then, as I said, my contact details are, you have them, so please don't be shy to reach out. It's taking a lot longer than it did when I tested it. I'm not sure if any of you have got an output already. But when we get, there we go. All right, so this is now your zeta decline, but it's the exponential version. So this is an estimate of what we expect the distribution to look like. So how many species are still shared as you compare more and more sites together. So it's logical here, your zeta diversity goes down the more sites you have. So the diversity is lower, there's less species that are shed across the whole area. And this is your zeta ratio, which is opposite of that. It's telling you how that ratio drops with distance, and these are your exponential and power laws, which I won't talk about in too much detail now. All right, and this is the different version. This is your Monte Carlo sampling. So this is taking it using your actual coordinates, and so we want to know how distance is included in the scenario. I'm not going to run this because you're going to have output exactly the same as this, but it will be based on your empirical data. So it will be based on the actual location of your site. So if you run that, you'll get something similar. Your zeta decay, if you go down to line 809 and run that. Right. I was having some trouble with my plot, so that was just clearing it. You shouldn't have to do that. Anyway. So your zeta decay, and all of the zeta functions, this is your sampling intensity. So the higher this number, the longer it's going to take to run. So I'm going to just make it really small for now. And also the number of orders that you do, the longer it's going to take. So your zeta decay, okay, that went a lot quicker because all right, it could be because the sample size is so much smaller. So if I change this down to 6, see if it runs. So yeah, you want to have as many sample sizes as possible. 1,000 is probably the lowest you should go. So for this exercise, okay, so I did still have that copy. I'm just going to do that and then run it again. So you should do at least 1,000. Depending on your processing speed, you could do more, but this is not ideal. All right, then you get your zeta decline with distance. Your zeta distance decay. So this is how strongly distance matters. So obviously with rare species, the further you go, the less of them you find. Whereas the common species, the further you go, the less it matters because they're everywhere. Okay, then this one here, this is, I know I'm rushing now, but I want to get to this fitting of the zeta with your MSGDM. Right, so that's 852. And it's important to set your seed here because it's a model that works on randomizing your input or the subset that it takes. If you don't set your seed, every time you run the model, you're going to get different results. So if you want to keep the same results to compare, here what I'm doing is I'm using the reduced variable. So if you didn't run that, section where I took out the ones that were highly correlated, then you'll have to change this for the name of the object before it was reduced. Telling it where my coordinates are. I'm setting it to, so this is zeta order 2, which is just turnover. So if I run that, hopefully it doesn't take too long. Okay, there we go. So it went very quickly, but it's only 100 samples, so it's not ideal. All right, so this return ice line returns the ice line estimates from the output. And let me see if I can move these windows a bit. You can use a bit better. You all should have, sorry, the font's a bit small or a bit large. It can't make up its mind. Ah, shoot. So. There we go. So this is the output that's telling us the relationship of beta diversity. So that's turnover, site-wise turnover for the different environmental variables. So you can see the one that, let's see the legend on the side here. On yours, you should be seeing there it is, right? The legend on the side here. So this one here is your observation sum. So it's by far the biggest informant. So the person who asked how do you deal with this bias. So the more observations you've got, that's what's causing the relationship the biggest. So if you take that out, you'll see that it actually changes this whole graph. So it's really important to note that. And so by taking that out, you've now removed that influence, and now you can interpret these relationships with the different environmental variables as an unbiased view of it. So hopefully you can read a bit more online on the website, if you are running out of time here. This is just explaining the variance. Oh, that's not too bad. So it's saying there's about 58% explained variance, which is probably because we've got the sample size in there, and you can see it's got a very big relationship. And the model output is basically the same as your linear model, your general linear model. So here are your different environmental variables, but because it's a spline, you've got these different slopes. So at different points along here, this is the relationship with environmental variable. So essentially, if it's very hot versus very cold, you're going to have a different pattern emerging. Okay, so the dissmapr function, it's got an embedded function called this run iSpline model. So I ran through all of the zeta div functions for you separately so that you could see what they do. But the dissmapr function takes that and wraps it into this run iSpline model where you can set the number of orders that you want, and it will do this for all of them. So if we take it from line 911 and we go all the way down to 935 and we run it, it will take a little bit longer, because what it's doing now is, instead of just running that one order, it's running orders 2 to 6. And it will take all that and summarize it for you to see how the relationship with your environmental variable changes with how rare the species is or not. So this example I've shown you now is your beta diversity, the typical one that you would use. But if you wanted to look at more common species, like I was saying in the beginning of the talk, that are driving ecosystem function, essentially, you can look at your higher order. So in this case, we put in what was it, up to order 6. So order 6 would be 6 comparison of 6 sites. So that beta number that you have is a number of species that are shared between 6 sites. But as I mentioned, this is your random sample, so it's only taking 100 sites to compare up to 6. So that's why we want that number to be bigger. There we go. So it's done. All right. And if we go down here and we plot it, so from line 943, we need patchwork to plot it, and looks horrendous. So let's see if I can drag it across. A little bit better. Amazing. Oh. We'll make it smaller so you can see. All right. So there you go. So now this is different colors for different orders. So for the temperature mean, it's more important for your higher order. So for orders 2 all the way down to 5, temperature has no role to play. until you get to order 6. Now, this could be a byproduct of the resolution of the environmental data that you put in. So that is something that you need to be cognizant of. But essentially, that is what the plot iceline function does in here. It's all explained on our website. So once again, you can go through this part here, Zeta with dissmap, and it will take you through all of that and explain exactly what the outputs are. What we didn't get to go through, the predict community turnover and the mapping of the bioregions, all of them are in the script with a lot of annotations so that you can do it at home. You can go onto our website and have a look there for more detailed information of what is going on with that. So yeah, sorry we ran out of time, but as I mentioned, my contact details are available, so please reach out, and I'd love to chat to you if you've got real data that you want to test this with.
Thank you, Sandra. That was amazing. Thank you for guiding us line by line through the script while also answering all the questions. So thank you. Really interesting, very informative. Turns out the Friday 13th was lucky for us after all. So just to wrap up, please let me just quickly share with you the next session that we'll be organizing next Friday about the producing colorblind friendly maps. We'll have Duccio Rocchini with us next week. So please do join us again. Spread the word to your colleagues and friends to sign up if they didn't already. And also just to prepare a little bit ahead of the session, if you want to just access the GitHub page of Duccio and then install some packages so you have everything ready for the hands-on session next week. So just thanks again to Sandra for everything, all the amazing work she did. And a reminder that you can find on BCubed website under the guide and tutorials section of the website, interesting materials that you can follow through at your own pace. And we'll also provide the recordings and the slides from today's session, so you can always go back and you have Sandra's details to contact her if you have additional questions. So please follow us on our social media platforms and keep an eye on the website, sign up for the newsletters if you want to, and of course you can get in touch with us using also that email address, info@bcube.eu. Certificates of attendance are available upon request, so just drop us a line and we'll try our best to accommodate all requests. So thank you again, Sandra, and thanks to everybody that made this session possible, to all the attendees. Hopefully we'll see you again next Friday, and enjoy the rest of your day. Have a lovely weekend and see you next time. Thank you.
Thanks, Christina, and thanks everyone for joining. I hope to be in contact soon.